And welcome again.
I'm doing it both.
Let the games begin.
Hey everyone, so thank you to Ilya and Enrico for doing their organization, and thanks to all of you for showing up here. And I certainly look forward to spending what sadly for me will only be 2 weeks with you, but I hope you can have your enjoyable time the rest of the weeks, and I look forward to all of your publications. Yes, so as Ilya and Enrico indicated, my name is Cole Miller. So first point of business, please do call me Cole. Not doctor, not professor, not Darth, although that would be kind of cool. So for those of you who don't know me, I mean, if you know me, you know that's what I like to be called. But there are basically two reasons why. One, if it wasn't already obvious, I'm a pretty informal guy, and I just generally prefer that. But the other thing, which is kind of more important, and I think may be an indication of the way it would be good to approach this entire summer program, is informality can be a good thing. I don't want it to be that you quake in terror when you get in the vicinity of Enrico, because he's such an imposing figure who has contributed so much. You want to be able to get to the stage where you can just ask him questions and say, well, wait a second, I don't really agree with that. I think that informality can help with that a little bit. Today, we're going to have the first of the three of my presentations, which I've been asked to give, and there are going to be three components to this. One is that we're going to talk a little bit about astrophysical reasoning. If you're like I was going into grad school and even much of the way through it, this is slightly different from the standard thing you might have encountered in classes. In classes, you tend to solve stuff exactly. In astrophysics, you can wave your hands a lot. And I'll try to show you how to do at least some of that in a productive fashion. The second bit will be some general aspects of gravitational waves. Like, what is it that can radiate gravitational waves? I'll try to explain this in an order of magnitude way, which can be a helpful way of going about things. And the third is that, although, as we heard, there won't be enough time to actually do my tutorials, we have some printouts that Annette very kindly made for me, and I'll hand them out, and we'll see if you can work on a few of them near the end, and then we'll sort of bring back together and talk about what you got. Now, one more thing before we go on, and here I want to kind of ask your permission. I think that it would be very useful to have as interactive an experience as possible. And with that in mind, what I would recommend is that at certain times you break into groups of, with this size people, maybe 5 or 6 people, so you can start discussing certain things. So that way you don't just have to listen to me drone on for an hour and a half solid. But I know that sometimes people aren't comfortable with that. Is that okay to do? Is that something you'd be all right with? Are you awake? Is there apathy? Okay. Yes. All right. Good. So we'll then go ahead and do that. And as I said, we're going to start with astrophysical reasoning. Now, my background, when I was an undergraduate at a little college you have never heard of, I was a mathematics major to begin with, but there were only 2 math professors, and therefore, after I took all of their math classes, I decided I wanted to do a bit more, and I took on a physics class instead. And now, since I have eventually gone into astrophysics, I've undergone an interesting personal evolution. That evolution is from somebody who was expected to prove things by God's rigor of mathematics to somebody who would occasionally run into this sort of thing and then do this. But astrophysics doesn't mean doing this all the time. Quite critically, what astrophysics does mean is looking at a given problem and trying to decide what is the most productive approach. Occasionally, it can be doing something with mathematical rigor. Sometimes it's doing something like that because this is good enough. Now, you're probably more used to the mathematical rigor aspect, and so what I wanted to spend maybe the first half hour today doing is going over some different aspects of order of magnitude thinking, and quite critically, why it is that knowing what you want to get out of a problem informs the approach that you take to that problem. Now, just out of curiosity, how many of you have in fact read my lecture notes for today? Okay, a decent number, but small enough that I can pretend that many of you have not, in fact, read this. Incidentally, I'm also going to be lecturing tomorrow and Friday. What I would appreciate from the students is if you were to read my notes in advance and come prepared with a question about them. What I'll do beginning tomorrow and at the beginning of Friday is I will ask for those questions to be discussed, and I'll make a list on the board. I want to do that because I hope that this will allow us to customize the approach, that I know what most interests you, and I will divert into that direction. Very good. Order of magnitude analysis. That's what it sounds like. Astronomy deals with a lot of orders of magnitude. There are very small things, very big things, very slow things, very fast things, and so on. It is actually quite important to be able to give a quick assessment of a problem. If you were to have a particular problem and immediately go for the most complex and rigorous approach, you could easily lose yourself in the weeds, whereas sometimes you can get insight very directly. Now, as we get an example of this, and those of you who read my notes will know what's coming, let's imagine that I have a water tank, okay? A filled water tank. And this water tank has the following dimensions. It is 97 centimeters deep, it is 103 centimeters wide, and it is 109 centimeters long. Filled water tank. Now suppose that I were to present you with this water tank, and I were to say to you, I would like to know the mass of the water in this filled tank with those dimensions to the nearest gram. Can somebody suggest how you would approach that problem? What would you do? I should mention I'm also going to ask a lot of questions. Sometimes you might doze off just before. Feel free at any point to ask me to repeat the question. Should I repeat the question? How would you calculate the mass of the water in this tank with these dimensions to the nearest gram?
With the density of the water?
You might take the density of the water and then you multiply the volume. Great. Certainly that would do it, right? But if you think about it a little carefully, you may realize that there are some interesting complexities that come up. What is the density of water? Anyone know that? 1 gram per cubic centimeter. Right, okay, so I guess what we're saying is all we have to do is take 1 and multiply it by this and this and this, and you've got the mass in grams, right? To the nearest gram. Do we, in fact, have that definitively? So, if we think about this, this is about 1 million, right? Give or take. Now, if you want the mass to the nearest gram, you need to know the mass to a part in 1,000,000. So is it in fact the case that the density of water is always 1.000000, etc. grams per cubic centimeter? What are some things that might alter the density of water? Just give me some examples. Pressure, the salinity, the temperature, maybe even where you're doing it, right? Because if you happen to be on some mountain, the surface gravity is enough different from what it is maybe at sea level that the amount of water you can fit in the tank is different. So the point I'm making here is that this apparently simple problem that I'm starting with is actually more complicated than that. If your goal is to figure out the mass to the nearest gram, you need a lot of information. Is it exactly pure distilled water, or is it seawater? What is the temperature, the pressure? Do you have any aspects of the container that we need to know about? But in contrast, let us suppose that all I want to know is whether you personally, with your own muscles on Earth, no fancy business, would be able to lift the tank over your head. Who thinks they could do it? If so, I have some athletic enterprises to suggest to you. Approximately, what is the mass if we're talking about water in a tank this size? Roughly, what is the mass?
It's a ton.
It's a ton. With 2 N's and an E? Grit. Yes. Oh, by the way, I should also mention that the class this size, if you wouldn't mind raising your hand before participating, I'll be able to focus a little bit more. The echoes are remarkable. Okay, so this is about 1,000,000 grams, about 1 metric ton, with 2 M's and an E, apparently. Not a chance unless you were born on Krypton. But the point is that we've got the same general setup, but in 2 different cases. In one, you can do the answer right away. A simple approximation. In the other case, you have to know a lot of information and do quite a detailed calculation. This is not very astrophysical. It is, however, a situation which arises a lot in astrophysics. Also, notice the second thing that we did is really easy compared to the first. all you have to do is say, well, I'm not going to actually even multiply this out. This is about 100, this is about 100, this is about 100. Is it close? Now, if it happened to come to 100 kilograms instead of 1,000 kilograms, it's possible that there are some people in this room who could actually lift that over their head. Not everyone, but somebody might be able to do it. So you need to do the calculation more carefully in that case. This is the advantage of approaching astrophysics using such calculations. It's quick, it's easy, and it tells you if you need to go a little farther. Let me now give an example, again from the notes, which is a bit more astrophysical. Let's suppose that I ask you to solve the sun. Now, a reasonable response would be a blank look, possibly followed by some drool, because I have not, in fact, given you enough information to tell you what I'm thinking about. So let's try a particular example. So we have a lot of people here. I would guess that most of the people in this room are in their 20s, more or less. In your age, in the time that you have existed upon this earth, have you ever seen the sun twice the radius it has now, or half the radius it has now? Probably you don't want to look at the sun. That'd be a bad idea. But in fact, it's true that it's not twice or half the radius that it has been in your lifetime at any point. But so far, we don't know if this is interesting or not. And therefore, we need to do a kind of calculation to say whether this is interesting. And one calculation you could do is you could say, well, what if there were nothing holding up the sun? It's just in the process of collapsing, how long would it take? Now, you can do a simple calculation to tell yourself that it would be about an hour. An hour is much less than any of your ages. That means this is something you need to explain. If you did the same calculation with a molecular cloud, the answer is much longer than your lifetime, even if it's in free fall. So again, it's this type of context that helps you out. If you were to pursue this, you could treat the sun as a spherical ball of gas. You could come up with the equation of hydrostatic equilibrium, and you would be able to convince yourself that there is, in fact, something opposing the collapse of the sun. So there's another easy, and this time astrophysical calculation. But if, in contrast, your interest is in knowing all aspects of the magnetic field of the sun, its evolution, behavior, structure, topology, and so on, you and hundreds of your best friends will work your entire careers and not answer that question. This is why it's important, in my opinion, if you're going to do any astrophysics, to be able to have flexibility. You need to be able to judge the right approach and then take that approach. One of the exciting things about astrophysics, for me, is that astrophysics involves so many types of physics. Think about just neutron stars, one of my very favorite objects. In neutron stars, all four fundamental forces play critical roles. There are aspects of condensed matter physics that are extreme. These are things that are superconducting superfluids with a transition temperature of 100 million freaking Kelvin. General relativity is important. Aspects of electromagnetism are very important. Nuclear physics is highly important. So this is an opportunity for you to learn many things. Now, any questions about that before I talk a little bit about the nature of creativity? Creativity is something that you can't bottle. Despite many instances of progress in computers, you do not yet have computers which are going to be independently creative. So I'm not going to claim that somehow I have a magic formula. But there are a couple of things that we can think about. Something that I remember first encountering when I was a little kid and I was going through some stuff with my mother is a suggestion that in some sense you can break creativity down into two stages. Again, not an algorithm. But those two stages would be as follows. Brainstorming. You have your creative thought. You let it loose. You don't self-censor when you come down with ideas for things. And then, after that is finished, critical thinking. So now you put on your hat and you try to kill those ideas dead. But you need to kill it in a clean way. Now, what I mean by that is, suppose you're trying to figure out what's causing a particular astrophysical phenomenon. You can come up with lots of cool ideas, but you want to be able to narrow down to the most promising ones. It's useful to think about broad scale things. Is this idea, number 17 on your list, does it produce enough energy to explain the phenomenon, for example? And if it misses by a lot, then you can say this is definitely not a candidate to explain the phenomenon. If it's close, or if the complication is difficult to figure out, then it's no good. Again, an example here, and we're going to do this much more extensively in just a minute. Let's suppose you would like to know what makes up the sun, right? And somebody has the idea that the sun is a giant solar mass ball of paper. How could you test this idea? The question you need to ask yourself is, what's the easiest way to do it? So let me give you an example of something that would not be an easy way to do it. You've heard so much about astroseismology, the oscillation modes of stars. This is one of the somewhat undersung contributions of the Kepler mission, famous for discovering so many exoplanets. It's been able to look at a lot of stars and see how they oscillate. So all you have to do is figure out the astroseismic modes of a solar mass worth of paper. Now you're going to do your calculating for a long time. And you might make a mistake, but even if you don't, convincing somebody is going to be kind of tough. You want something which is a crisper way of testing things. So as I say, unless there are questions now, I would like to suggest that we have the first of our group activities. So you'll find 5 or 6 people around you. And what I'd like to do is try to figure out the fundamental power source of the sun. Now we know what it is. Somebody say what powers the sun. Nuclear fusion. Okay, we know that. Pretend you didn't. So the first step here will be to group you together and have fun with this, obviously, and to come up with possible fundamental power sources of the sun. And then after you have done this a little bit, I'll sort of call on you group by group. We'll get a list. And I say, have fun. Don't have to be serious about this. After we're done with the list, we'll try to quickly go through and ask, how would we kill the ones that are definitely wrong? So is the general idea clear? First, you'll come up with a list of power sources, and I'll kind of go one possibility per group. We'll see what kind of list we can get, and then we'll see how many we can kill. All right, go for it. Wonderful video.
Someone asked me, how do you choose what one to do or what one to do? Well, I calculated the product. How much one is your object to? And what's the problem? It's very difficult to use Mars computers, so I know.
I don't make your own problem. I do a lot of times I will also especially like it'll probably be something that like white side have a little bit of wood. And as an example, stuff like that from my organization.
Actually, I'll make yeah, and then on the other side, like, you know, not gonna let someone else work on it.
It is. The other thing which is certainly different modes than I have been able to use is more and more use of genre proposals. I'm feeling more and more like my life is but I feel people like fire hard to learn something like there's also a tendency to want to change something and I like it if there were more people who supposedly did or studied calculus. How do you do it? So I'll give another couple minutes. Yeah, could you restart that?
I was like, you know, this era kind of trying to long and some of your ones are like,
All right, everyone. Yes. Sorry to interrupt, but it sounds like there's some very interesting and creative ideas. As I said, what I'd like to do is essentially one suggestion per group. We'll just go through all the groups and keep going until we run out of ideas. And I'll also share with you an evil professor trick, which is that groups consist of multiple individuals, and the second time your group is around, let's have a different spokesperson. That way you get the sort of multiple interactions going. Oh yeah, I know, that's terrifying. All right. Okay, who would like to start? Hand raised, please. Yes?
Spin down energy.
What?
Spin down energy.
Spin down energy, all right. Another group.
So we have like hamsters on the treadmill?
Yes! Hamsters! All right. Outstanding. So one per group, remember? So
Yeah, oh, we're
Yeah.
you're a different group? All right, yes.
Yeah. Dark matter annihilation.
Dark matter annihilation. So I guess a lot of people had that, yes.
It's a big lemon with copper and zinc nails, and then
It's a solid, so there's no powering. It's just so hot that it's not collapsing it.
So it's cooling off there.
Yep.
Yeah.
It's highly heated up by the planets in the solar system.
Right. Okay. Groups. Yes.
It's a big ball of burning coal. COLE.
Seems a little harsh. Are there groups that have not contributed yet?
God.
All right.
Prove that way.
God did it. It's one of the most popular theories in the United States.
Increasing black hole in the middle.
Okay.
A white hole.
All right. Any groups that have not contributed yet? Okay, then we're on to round 2. One per group again until we run out.
Chemical reactions.
Okay.
Shock heating.
Shock heating. Okay.
Thermal contraction.
Thermal contraction. Okay.
Fission.
Sorry, there's some background noise here. What is it?
Fusion.
Fusion. Yeah.
Like a heavy metal, like compression of gravity with friction. Yeah.
Yes, just heavy metal.
Iron made it to the center. Down the laser.
Excellent.
Down the laser. Down the laser Metallica.
Any others for groups that haven't contributed a second time? All right. Any others, period? Yes.
Aliens.
Aliens.
Of course.
Lots of layers rubbing against each other and creating friction.
Okay. I think we're on to round 3, aren't we? Okay, any round 3ers?
Recombination.
Recombination? Pardon? Rumstraw?
Lots of fluctuations.
Vibrating strings.
You could have a binary sparring together in them.
You could write a paper about that.
Anything else?
Continuously flowing rivers of hot gas. Biofuel sources from dead solar dinosaurs. From the solar dinosaurs.
Oh, so it's got to be solar dinosaurs? So for what it's worth, and this is a marvelously creative list, there are at least 2 astrophysically relevant mechanisms that have not been mentioned yet. To give you an idea of the variety we have. Dan?
Magnetic fields.
Yeah, it's one of them. You may know this story. If not, well, you're young and you're going to have to laugh anyway because I'm the instructor. The standard story is that if you go to an astrophysics colloquium and sleep through the entire thing because Chris Pryor is giving it, then, and at the end, you want to ask an intelligent sounding question, you just say, what about magnetic fields? So, unfortunately, however, more and more people are working with magnetic fields these days, so you still look like an idiot. Okay, that's a pretty good list. And by the way, the other that I had in mind, yes?
Crystallization of phase separation.
Was that, exactly, which is something that can have relevance in some situations. Okay, so we'll add that one, and then we will end. Yep, I would say that this is the perfect number of possibilities. Okay, now, we're not going to do the group thing necessarily. Let's just call this out. Is there any one of these that you could rule out? And if so, how would you do it?
Hamsters.
How would you rule out hamsters? So the clean way, right? You know, what's the very best way you can do it?
Get a bunch of hamsters.
So you want to do the experiment with the solar mass of hamsters? Yeah. The Society for Prevention of Cruelty to Animals might have a word for you. Yes, go ahead.
Just figure out how hot it would be at the center and think about
How quickly the hamster burns.
But the thing is that if you want to extract energy from hamsters, they don't have to be alive.
energy then.
So what's the cleanest way to rule out hamsters?
Energy.
Yeah, energy output.
Arm raised, please. Otherwise, I have no idea what you're saying. Yes.
Energy.
Energy.
I mean, they cannot produce that amount of energy.
Yes. To be clear about the question, is it that they cannot produce that amount of total energy or energy per time?
Per time.
And stunningly, if you do the calculation, what you discover is that per mass, hamsters produce something on the order of 1,000,000 times as much energy as the sun does per time. Yeah. Hamsters, if you want to do this calculation, and if you know what the quantity is, emit significantly more than their own Eddington luminosity. Yes?
I mean, unless we're transporting hamsters in and out of the center of the sun,
Yes.
you have to consider how quickly they breed and what is their lifespan, and how
Yeah.
long we've seen the sun producing the energy. So even if the energy dot matches, the total integrated energy that you could get from any population of hamsters couldn't.
And in fact, so in fact, energy is a good way of doing this. But in fact, it turns out, yes, that it's the energy per mass, not energy per mass per time, but the energy per mass that is the killer. In fact, it kills all chemical mechanisms. Because as it turns out, having hamsters on a treadmill or having burning paper or burning gasoline all amounts to about the same thing, and it's a factor of 1 billion short. So this is an example of something where you can have a clean kill. Now some of the others, like God or aliens, are a little challenging because you don't specify a mechanism. There's at least one mechanism up here which has enough energy total, and that's, well, so of course fusion, which you know is ultimately the right answer, but also fission has enough energy. Is there any problem with that then? So let's suppose what you've got, because I know one of your first things would be, well, sun doesn't have the right composition. Fine. But let's suppose the sun is actually a gigantic ball of uranium covered by a thin layer with the composition we actually see. Is there any way of ruling this out as the energy source for the sun?
Time dependence.
Time dependence? What particular time dependence would you have in mind?
If it was fission, then it should decay.
Okay, so is that what would happen? Suppose you put together a solar mass of uranium.
I think it's actually the other way around. Because fission is critical and it goes boom.
Yes, so there would be a very sharp spike of energy generation leading to nothing afterwards. So the stability. So in fact, these two things, we're not going to do it because we don't have time, but if you were to go through all of these mechanisms that actually make serious predictions and figure out which is going to give you stable energy production and total amount of energy with the solar mass that you have, you'd find out that the only viable one is fusion, and then the black hole in the middle, there's a little bit of a subtlety. The sun would not look like what it does. So if you have unlimited amounts of time, you can actually try to go through this. But this is a good list. Well done. Then the last thing I just want to mention in terms of order of magnitude estimates is there are a lot of times when the order of magnitude estimate you can do in a given field of astrophysics can be sped up and made much more efficient if you know certain quantities. I give an example in the notes. Anybody happen to know how fast the Earth moves in its orbit around the sun?
Like 1,000 kilometers a second?
Yeah, 30 kilometers a second, yeah. So why do I mention this? Because that's the speed that you move at 1 AU around one solar mass object. And what this means is that with that bit of information, you can shortcut a whole lot of calculations that involve dynamics. What's the orbital speed 1 parsec away from the center of a globular cluster of 10 to the 5 solar masses? Right? But if you know things like how many AUs in a parsec, you can do this very, very quickly. And this is helpful. It actually cuts down on your errors because you don't have to use freaking G all the time, like remembering what units is and what the formulae are. You can do scalings and things like this. Now, the numbers that are important to you will depend on your field, of course. But this is something to keep in mind. It means that your order of magnitude calculations can be fast, and you can impress people at conferences. Yes?
So we were looking at the spin down, and we considered a white dwarf going in a 1 second period in the center. It looks like it has enough energy, and since I haven't said how it's losing its spin down energy, but imagine there's some kind of friction, it seems like you can't rule that one out either.
It's true. In the same way that you would be able to do similar things if you have, for example, accretion onto a neutron star or to a black hole in the center. That would potentially have enough energy. So
Yeah.
those take more effort.
But those I can rule out through the fact that if you have a neutron star there, you're going to emit neutrinos. So I have a neutrino.
But we've detected neutrinos from the sun.
So I lose on the neutrino side. But the white dwarf one, I'm not sure you can rule out.
So the white dwarf one, so you say it can emit 10 to the 51 ergs eventually?
Yeah. And so 1 second, moment of inertia is 10 to 51. So.
All right. There you go. You got a paper to write.
Well, then you'd have a lack of neutrinos.
What?
You wouldn't have solar neutrinos. The same problem reverse.
Yeah. But those become more subtle. Yes?
Might you see weird burning products at the surface of the sun if it was accretion powered? Because I remember with TZO.
Yeah. That's the idea. This is how some people think they can identify Thorne-Zitkov objects. And there's at least one candidate, as you know, which has precisely it has at least in the ballpark of the abundance distribution. That, in fact, a Thorne-Zitkov object would be a giant. That was the most immediate thing that Oppenheimer actually found when he looked at Landau's suggestion that the sun might be powered by a half solar mass or less neutron star in the center. Yeah. Good job, everyone. Shall we move on to gravitational waves? All right. So with gravitational waves, I want to say a few opening remarks about gravitational waves. Then we can go on. Gravitational waves are unusual. They're very, very weak. They're so weak that they pass through things like they're not there. And it also means that there are no sources in the sky so bright that you can detect them easily without knowing what they are. In electromagnetic astronomy, we have examples, for example, the sun. You don't need to understand nuclear fusion in order to detect the sun. And there are lots of other objects like that in the sky. If you don't live in a city, you might know them as stars. So you can actually look at these and see these and wonder about them and kind of gradually develop your understanding. With gravitational waves, however, because they're so weak, it is thought that the majority of sources that are seen, even with very sensitive instruments, such as LIGO Virgo, GEO 600 Kagra, and LIGO India, are going to be weak enough that you need to have some idea of what they look like before you can detect them at all. That is to say, you need a template. And I'm not going to be talking so much about that, but it's one of the differences that exists for gravitational radiation. We'd also ideally like to have a circumstance in which gravitational waves are going to be detected from sources we did not anticipate. Now, to some extent, this has already happened. Depending on who you talk to, it was or was not a surprise that we saw 30 solar mass black holes. It's twice as massive as any we know for sure in our galaxy. So that's kind of interesting. But what about the really weird stuff? What about a 1.0 solar mass compact object? What about cosmic strings? What about the things we just don't know at all? And therefore, for the rest of my lecture today, and then the one tomorrow and on Friday, we're going to talk about different aspects of gravitational wave sources. The first thing we're going to do, and that's what we'll more or less end with in terms of the content here before I distribute some questions for you to work on, is the basics of gravitational waves and indeed of radiation. So we can start with something that is basic enough that it works for both gravitational radiation and electromagnetic radiation. The nature of radiation itself. Well, one thing you can say, and I will kind of assert this, so the flux, so this would be energy per area per time that you get in radiation is going to be proportional to the square of the associated amplitude. This might be the electric field if you're talking about electromagnetic radiation, and it might be something called the strain, which many of you know about for gravitational radiation, but it is in fact proportional to the square of this amplitude. If we think about the luminosity is going to be proportional to r squared, where r is the distance from the source, times the flux, thereby giving you the lovely fact that the energy per time is the energy per area per time times the area. Now notice the proportionality factors here. If I were being really astrophysical, then I would do something like this, the indispensable squiggle symbol, which essentially means that I'm not worrying about a lot of the factors here. So it might be 4 pi or it might not be. It doesn't have to be a spherically symmetric source, but it at least gives you the general idea that, all else being equal, you expect that a given flux times some area is going to give you a luminosity. If it's a radiation field, it has to be able to carry energy to a very, very large distance, an arbitrarily large distance, which we sometimes simplify saying infinity, although when I've said that occasionally people start twitching because they don't like infinities in astronomy or physics. We want to be able to carry this to a very large distance. Now with that in mind, we can ask ourselves, what power of the distance r must F go as for this to be able to carry finite energy to infinity? It has to be 1 over r squared. If it, for example, were 1 over r to the 4th, then as r goes up without bound, the luminosity would drop without bound. So this would not carry energy to infinity. Now, believe it or not, this already gives us some remarkable possibilities for insights about what it is that can and cannot produce gravitational radiation that carries to infinity, or for that matter, electromagnetic radiation. To do that, let's first think about the amplitude being the electric field. Okay? Now let's suppose that what we've got is a single charge, and we ask about the electric field, the distance r from this charge. Let's say it has some charge q. So not bothering about factors of 4 pi or whatever, the electric field is going to be proportional to, how is it going to depend on, say, q and r?
Q over r squared.
So this is going to be something like q over r squared. Can this electric field carry energy to infinity by radiation? Q over r squared. Squared goes like 1 over r to the 4th times r squared. So that would mean that L from this, if you could even write it that way, would go like r squared, say 1 over r squared, it's proportional, squared, or like 1 over r squared. Okay, but this is only the monopolar electric field. How would, say, the dipolar electric field depend on the radius? So 1 over r cubed, so that's even worse, right? Well, maybe we should go to quadrupole. How does the quadrupole depend on r? 1 over r to the 4th. So that doesn't work, does it? So what that tells us, actually, is that there's no static field which can carry energy to infinity. In order to get radiation, you have to have something varying. Now, if you do this, and you need to do it in some detail, you will find that the field you get when you have a variation of the source, in fact, goes like, so the effective amplitude goes like 1 over r. And so when you square that and multiply it by this, you get, in fact, what you need. So our first bit of insight is that radiation implies variation. It's not bad for an order of magnitude calculation, is it? But now we can actually go farther than that. What do we mean by variation? So something about the source has to vary. There are different ways you can characterize your source. One way that turns out to be very helpful indeed is to phrase the properties of the source in terms of multipoles. So let's begin with a monopole. Now, initially what we're going to do is we're going to work with electromagnetism. We're not going to do gravitational radiation quite yet. So let's say that we've got something that has a charge density of rho e. So it's your favorite charge unit per volume. Now the monopole moment here, they're different. You can define this in different ways, but the one which we're going to use is, this is the integral over whatever the volume of your source is of d cubed r times rho e. And for this and the other things which we're about to do, what I would like you to consider is the case where we have a finite source with a bounded volume, and we're thinking about observing this from very, very far away. And there's nothing else. It's the usual simplifications. There's nothing interacting with the source. It's by itself. So that's what we're going to think of. Now, if we were to do this integral, what would it actually be? And again, remember, the hand raised if you want to have an answer. What is this integral?
The total charge enclosed by the volume?
Yeah. So this is going to be, let's call it Q, right? So this is the total charge in that volume. Now, okay, fine. So this is our monopole. But here's a question for you. Remembering that, based on the arguments we have here, we need variation. If you've got a completely isolated source, is the total electric charge in that source, can it vary? So then we can answer, can we have electric monopolar radiation? You can't vary that. So that means there it is. All right, great. So we've totally ruled out monopolar radiation. Yay. So now what we're going to do is we're going to do what is called the so-called electric dipole. And I am putting scare quotes around this because when we talk about gravitational radiation, we're going to use the same terminology even though it won't have anything to do with electric fields. The electric dipole is, again, your integral over the volume of d cubed r time, and this is now rho e r. Now how about this? Can this vary? Is this something? Is there any system you can imagine with electric charges where this could change with time? Is that okay? Yeah. And when you do these types of analyses, it's actually helpful to think of specific examples. Let's think about not an atom, but a classical setup where you have a proton and an electron, and the electron is moving around the proton. So not an atom, but it's just something that is classically moving around. You could convince yourself this does in fact vary for that system. So that means that although this does not give you any radiation, this could give you radiation. Doesn't have to. Your system might have a symmetry such that this does not actually happen to vary, but it could. If you then go to another thing, you have the so-called magnetic dipole. And that would be the integral again over your volume of d cubed r rho e, and then this is going to be r cross v. So these are the velocities of the charges. If you look at this, you find that this also can vary. That's all fine. Now, as it happens, typically, although you can keep going quadrupole, octupole, hexadecapole, whatever the third two pole is, it tends to be that the lowest order multipole that can vary is going to dominate your radiation. Also, and this is another kind of order of magnitude thing, if your system is moving non-relativistically so that V is much less than C, this tends to be much smaller than this. Yeah, I'm saying tendency because, again, you could have a system where this is almost canceled out and this isn't. But this is sort of the rough thing you can think of. Great. So we understand, based on this, if you're thinking about electromagnetic radiation, no monopolar radiation, but you could have either one of these dipole radiations. But we're mostly interested in gravitational radiation, and so let's do that next. So now what we're talking about is we'll have, this call it rho, and this is now the mass energy density. If we take our mass energy density and do the same thing, we'll first look at the monopole and an exact analogy. We have the d cubed r, and now we have rho. So what do you think? What is this that I have just written up there?
The total mass energy.
Total mass energy. So this, and remember, it doesn't have to be just mass. As you say, it's the total mass energy. Can that vary for an isolated system? So we can cross this off, right? This is not going to produce radiation. So no luck with that. Now we're going to go for the so-called electric dipole. And again, we're just going to use the same formula. We're not implying that electric fields are involved here. So if we do that, then we do r here and d cubed r. And then now we have rho r. What is this? So it's related. It's very related.
Not quite.
Not quite, but it's very related, and keep that thought.
Center of mass.
So this is the center of mass. But, and now this is where your point comes in. And think very carefully. Can this vary? Can it change its value with time?
Not if you're in the frame of the object that's moving.
That's a key point. And implicit in what you said is that it, of course, could vary in a frame where you are not in the reference frame of the center of mass. If it happens that the whole system is moving with respect to you, it can change with time. But you can boost into a frame in which it is absolutely unchanging. So this means we actually need to add a little additional insight to our evaluation of whether the gravitational dipole can change and give us radiation. You can convince yourself that whether there is radiation has to be a statement that is agreed upon by everyone. We don't have a quantum theory of gravity, but for myself, I find it helpful to think in the following way. If there were a quantum theory of gravity, we might be confident that there are things called gravitons that are emitted whenever there is radiation. In the same way that you can count photons going by, and everyone has to agree that after something has happened, you have a certain number of photons, you should be able to do the same thing with gravitational radiation and gravitons. So, your observer who is riding along with the center of mass at a distance, who sees no change whatsoever and cannot possibly see radiation, everyone has to agree with that observer.
Does that mean in weird biometric theories or things where there's a condensed field that gives you sort of an ether, you get dipole or gravitational radiation because there is a preferred frame, and if your center of mass is moving, then...
It's a good question. So I don't know much about those theories, but I think there are two possibilities. One is that there would be a preferred frame, and the other is that the equivalent of this, that would be the dipole thing, isn't conserved, that it doesn't relate directly to a center of mass. I don't know which it would be, but I think one or the two would have to be the case. Okay, fine. So this doesn't work either. So now let's go to our magnetic dipole, and we have our V, D cubed R, rho, and now R cross V. What is this?
Momentum.
Angular momentum. If it's an isolated system, will the angular momentum be changing? So that doesn't work. You actually have to go to the quadrupole. Now, the mass quadrupole is something that you end up having a tensor. You have your d cubed r, rho, and you might write it as an ri, rj, or these could say take the spatial components. Anyone know what that is? Or at least related to? Moment of inertia. It's related to a moment of inertia. Now, I'm not claiming that you're going to be able to go from this and calculate your actual gravitational radiation, but if you work that out, you can understand that it can change. So unlike these three things. So radiation could come from quadrupole or higher orders, but not any lower orders. This is an interesting difference between gravitational radiation and electromagnetic radiation, and also, by the way, and just sort of giving you a reference you can follow up, it, among other things, tells you that if there's a quantum particle carrying this, it has to be spin 2, unlike the spin 1 photon, which carries electromagnetic radiation. All right, but why do we go through this? Okay, the basic reason is that we want to be able to get insight about what could produce gravitational radiation and what can't. So let me give you a particular thing. You tell me whether it could produce radiation. Let's suppose that you've got a tremendously energetic event. A supernova, a spherically symmetric supernova that blasts things out in a spherically symmetric way and collapses into a black hole, all spherically symmetric. How much gravitational radiation is going to be produced by that? Zero. Absolutely nothing whatsoever. It doesn't matter if it produces 10 to the 53 ergs worth of neutrinos. Zero gravitational radiation. This is related to something called Birkhoff's theorem, which you may have heard of, or at least the Newtonian equivalent. Anything spherically symmetric acts as if it has all of its gravity concentrated in the central point. So if you were way outside of the supernova and you had a shielded spacecraft and were using your very sensitive gravity meter, you would see absolutely no change whatsoever. No gravitational radiation. That tells us that any gravitational radiation from supernovae must come from asymmetries. And those asymmetries have to be determined by very complex simulations. Chris Fryer is one of the world's experts on this. And unfortunately, the difficulty of the calculation is substantial. People have worked on it for decades. But it's looking like only a tiny, tiny fraction could possibly be emitted. Okay, number 2. Yes?
So if I'm a devil's advocate and I look at that equation, I say, well, during a spherically symmetric collapse or expansion, that will change. The moment of inertia is changing.
This will change.
Yes.
So it won't, because you have spherical symmetry. Spherical symmetry actually means that doesn't change at all. Yeah.
The moment of inertia, if I have a spherical shell and I make it smaller, the moment of inertia does change.
That's because
so there must be like a minus 1/3 r squared. Or something
no, there isn't. So the reason there isn't is if you got something which is spherically symmetric, remember that Ri has a sign to it. So that means that the part here and the part here exactly cancel. So when I'm talking about the moment of inertia, I was a little loose. This is something that's related to in an equation way, but it is not actually the moment of inertia. Good point. Okay, so next possibility. Let's suppose you've got a neutron star. One of my favorite objects again. Suppose your neutron star is completely axisymmetric and rotates around that axis. Is it going to radiate any gravitational radiation? Again, unfortunately, no. This already allows us to narrow down very substantially on the possible sources of gravitational radiation in the universe. And the people who do this sort of thing, so the LIGO type people, and also people who work in other frequencies of gravitational radiation, have basically decided on 4 categories of sources that can radiate gravitational radiation. One is binaries, and I assume you know about the LIGO events. If not, congratulations on waking up from your coma. Binaries are the easiest way to have a variable quadrupolar moment. A second possibility is something which is often called continuous. So we're talking about an axisymmetric neutron star not being able to emit any gravitational waves, but if it has a lump on it, or a mountain or something like that, in principle, it could radiate gravitational waves. The third is a burst. Now, the classic example of this is a supernova, which even if only a very small fraction, like 1/1000th or even less, of the total energy goes into gravitational radiation, if it's close enough to us, like in our own galaxy, could be seen. For the people who do the analysis, this also takes on a different meaning, which is any unmodeled excess in the otherwise noisy gravitational wave spectrum they're taking. So they want to be able to detect things that they don't anticipate. And this is a possibility of doing it. And the last one is stochastic. So stochastic gravitational radiation comes from a set of sources. It could be lots of different sources that are individually unresolved. The sexiest example of this would be gravitational radiation from the very early universe. You may remember, for example, in 2014, the BICEP2 team announced that they had found what is called B-mode polarization in the cosmic microwave background. And although that likely turned out to be dust, that is an example of something where there are lots of different individual sources that add up. A less sexy example, but still one that is important, would be the collection of perhaps 100 million double white dwarf binaries in our galaxy, most of which will not be individually visible to something like the LISA space-based detector. Some at high frequency will be, but most of them will not, but they add to form a kind of a collective background. And of course, you also have, for pulsar timing arrays, the supermassive black hole binaries, which are likely to come in as a stochastic haze rather than initially being detected as individual sources. So these are the different categories. Any thoughts or questions about that? Okay, in that case, what I would like to do, and I have enough for the students here, but you perhaps can share this with your friendly neighborhood postdocs or professors. This is the first set of tutorial problems. I'm not going to have time to do them all. I'm thinking of maybe you can work on this for maybe 20 minutes in your groups, and then we can perhaps talk about them, bring things back. My suggestion is that you focus on the non-quantitative ones. These would be numbers 1, 2, and 4. Each student gets a copy. There should be I think that should be the totality of it. And just talk in your groups. Again, I suggest 1, 2, and 4. If you want to do 3 and 5, you can, of course, try that as well.
The thing I'm sure about the case, there's
Right, so we'll just assume that rho is just all over.
It's 85 and this is actually
I like to talk about
But, so Chris,
oh, sorry. Okay. What is the maximum per day?
We were talking about, you already assumed that. I got the
I'm slow.
So really, because of the,
I'll get that out of
oh, because of the it's in also up there. I don't know why we're having
plug in the road. And again, it's hard to not so looking at this way. Yeah. First pulse to me, but I don't actually care about that. How much of the healing could be not that much. Okay, maybe this is single star. So I think
Right. What I think is funny.
one of the radius of the sun. So
dynamic mode, I guess.
So you see So something that can have really high frequencies and low radius.
Yeah, it's true.
So even though it's not
But what about that?
frequencies. So I guess I kind of qualitatively. That's why
So yes, because
Oh yeah. So it's really small. It kind of took
basically such small star has a higher.
also if you have the same
Yeah, it's the same density. Oh, but you didn't have to last number two. I guarantee you, you're just one of the yeah.
He invited us to do something with that.
Yeah, I think so because yeah, so first they're talking to the density all the time.
Yeah, is that right that ego is one of the hardest? What do you do that
We're gonna have some cancellation.
Yeah, no, I think pressure should be so force is mass acceleration. So
Yeah, I might be wrong. No, it makes sense. But what we're talking about when we're speaking about calculation, we're speaking about
that's correct. An article by from like 20 years ago that this general thing of the universe one of the things we're going to make yeah, so you've got something like
but I wonder what
every
that definitely makes sense.
If you're losing the square
I haven't
so now I need something order. This one has to be this one. So I need to have 10% of the mass. 1% of the mass.
Sorry to interrupt again. I hope you have the possibility, if you wish, to enjoy these problems on your own time. But we do want to be able to get done at noon so that we can hear some of the initial presentations of the projects. Okay, any group want to start with number 1? Any thoughts about things that are actually powered by some of these mechanisms, not including aliens or God or hamsters?
Short gamma ray bursts come from binary and spiral.
Okay, binary and spiral probably produce short gamma ray bursts. We'll determine this when we get the gravitational wave detection for sure. Okay, another group, another mechanism that they want to suggest is actually powering a real astronomical object.
Cooling of white dwarfs.
Yeah, absolutely. White dwarfs do not have an internal energy source other than their cooling and gradual gravitational settling. Another group, another real power source. Supernova, okay. All right. Anything else? So what one per person. Magnetars are powered by what? Magnetic fields, yes. Anything else?
The Crab Nebula, the spin down.
The Crab Nebula is in fact powered by spin down, yeah. Anything else?
Black holes and quasars.
Black holes and quasars is nice, the accretion power. Okay, anything else? All right.
Again, short gamma ray bursts, black hole in the middle.
Well, yes. That's right. At the end part of the gamma ray burst, if you produce a black hole, you are powering it by having matter fall onto it. Gravitational contraction powers protostars, not nuclear fusion. The Earth is kept hot in its center by a combination of radioactive decay and crystallization. And there are a few others like that as well. So the point I'm making here is, I hope you had fun making this list. But it's also something which, with a few exceptions, like hamsters and God, you might want to keep in mind if you're trying to explain an astronomical phenomenon. How many of you, anyone who hasn't spoken yet, did number 2 by any chance? Yes.
What do you want me to say?
Yes, please.
Okay. So for P, hydrostatic equilibrium tells you that P is roughly gm squared over r to the 4th, which is the force per unit area.
Yep, so just to elaborate on that, force, gm squared over r squared, area r squared, okay?
Rho is m over r cubed. So you can approximate CPD rho as P over rho. Let's take the square root and then show that you crank through it and then you show that r over the sound speed is equal to rho g to the minus 1/2.
Yeah. How would you get something that has a higher frequency than this? Like a much higher frequency. Make it compact, like a neutron star? The students in my grad classes start learning that neutron star is the correct answer to everything. But a neutron star would actually have the same considerations apply. And so with a slightly different prefactor, you'd actually get about the same answer. Is there anything you can think of that would give you a frequency much higher than square root of gm over r? Well, if you can't quite think about that, then, and of course, one more thing. So, this is the speed. So the frequency is that divided by the size, so gm over r cubed. Now, want to see a magic trick? This is awesome, I tell you. I am basically a bag of water. And as a bag of water, I have a density of about 1 gram per cubic centimeter. That means that if you work this out, the maximum frequency you can have from any of these mechanisms, so oscillations or rotation or maybe a binary, that I could possibly have is approximately 1 per few hours. But watch this. Are you ready? Ooh, faster than once per hour. How did I imagine that? What's the big difference between me and a star or a neutron star or something like that? Don't say I'm not a star. What is the main characteristic, the critical characteristic of a star that I'm missing?
You are not self-gravitating.
I am not self-gravitating, yes. I may have been putting on some food, some pounds by the delicious trip through Europe I just took, but I am not self-gravitating. As a result, these considerations don't apply. So if you have something that is not self-gravitating, you can violate this limit, but if it is self-gravitating, it's more or less going to adhere to that limit. Now, something I didn't get to today, but is in the notes that I do recommend you read, is this tells us immediately what kinds of objects you might be able to get in certain frequency bands for gravitational radiation. For example, if you're going to be looking with LIGO, let's say right now LIGO is starting at maybe 30 hertz and goes to 1,000 or 2,000 depending on your measure of these things. There are only two types of individual objects in the universe that can do this, black holes and neutron stars. You can't even make it with white dwarfs. They're not compact enough. When you get to something like LISA can, in fact, see white dwarfs because it's a much lower frequency. These are the types of considerations allowed to zero in. Did anybody get to Dr. Singh's expose of the LIGO team for the frogs they are? Did anybody look into problem number 4? Yes, go ahead.
Every way we read that problem, it came down to the fact that the two ends of the detectors just have to be farther apart than the wavelength of a gravitational wave.
I see, but the problem is they aren't. So 4 kilometers is actually considerably less than the wavelength of the waves that is being detected by LIGO. So if LIGO, let's say 1,000 hertz, the wavelength, so the speed of light is 300,000 kilometers per second, the wavelength is 300 kilometers, which is much bigger than the 4 kilometer size of LIGO. So they were cheating, weren't they? Any other thoughts? Or should we take this to the international press?
I know this is a classic kind of argument, but this treats it like a ruler rather than a stopwatch to some degree. So even if the wavelength of light is stretched to squeeze, the time that it takes for the light to travel down one arm compared to the other is still going to be different.
And that, for me, is the easiest way for me to understand this particular question. To simply restate what you said, if you accept that the speed of light is going to be constant, and this is as close to a vacuum as you need to be, if the actual distance is changing, increasing and decreasing, the time needed for, let's say, the crest of a wave to go from the middle station to the end station and back will be longer if it's stretched, shorter if it's squished. So that means that if you ask, when are the crests coming back, they're not going to match up in the same way as they were when the arms were undisturbed. But if you want to go into more detail than this, I believe Schutz's book, The First Course in General Relativity, has a derivation of this that involves metrics and things. So this is something that I definitely suggest you look into, but it is possible, just possible, that the LIGO team are honest. Okay, any other thoughts or questions about this? Yes?
In number 4, doesn't this sort of apply to if there were scalar modes coming through and not, bending one arm, stretching one arm differently?
So if you're talking about something as scalar mode, and this is interesting because we always want to be open-minded. One of the points of LIGO is to test general relativity. General relativity predicts certain modes, not including scalar modes. If you have something that were to, let's say, change the size of something spherically, you might ask, how would you be able to measure that? And the answer there is that if you look at the actual atomic bonds, those are also being shifted. And the shifting of the atomic bonds means that you're changing the energies of the atoms. So that kind of underlies the basic idea that Joe Weber initially had at the University of Maryland, which is to be able to look at steel bars, so not spheres, but steel bars. And that changing, since the atomic bomb sizes would be changing as the gravitational waves go by, will allow there to be an actual detection of vibration. So
would LIGO be blind to that?
LIGO would be, so somebody who knows more about LIGO, my guess is that LIGO would be blind to this. Can anybody confirm or deny that? It's certainly the case that if the crests are coming back in the same way, the pattern of interference is not going to be changed. There'll be a slight timing difference, but the pattern won't change. So I think it would be very tough.
Sorry, what was the? I missed the first.
So the question is, could LIGO see scalar modes? And my guess is no.
Yeah, I think we're literally insensitive to scalar modes.
Yeah.
So you're only sensitive to scalar modes in a very indirect sense, in the sense that if there is additional energy loss from a source in scalar modes on top of some modes you can detect,
okay,
then you can see that the frequency evolution of the waves is different than what you expect, because there's another mechanism of energy loss. So you transition, for example, through an inspirer faster because there's some other energy being lost in scalar modes. So there's sort of only this indirect.
That makes sense. But for something like LIGO, it would be insensitive. And I guess something that I should have thought of as a relation to that is, if you look at the L shape, and you have, suppose, a mode that comes in directly 45 degrees between the two, LIGO is insensitive to that. Can't see it all at that detector. Okay, now one last thing before I hand it over to Enrico is that I think I gave a misleading answer to a previous question, and so I want to remedy that. And that comes down to the question of what this actually is. So, the thing that I incorrectly said is that this would in fact be 0 for a sphere. It isn't. Because if you have the diagonal elements, those are not going to cancel out if you go to opposite sides of the sphere. My apologies for saying that. It is like Will said, we actually need to use the so-called reduced quadrupolar moment, minus 1/2 r squared. That is actually 0. So that's not obvious from what I've set up here. So, sorry about that. Anything else before we start hearing about the project? Right.
Actually, maybe we can take, if you need to stretch their legs, etc., we can take a few minute break before starting with the project, so I can help you set this up.
Okay.
Thank you. That was awesome.
You want me to erase this? Or?
Nah, we'll put this thing down.
Okay.
Do you know how to put this thing down?
I do.